Thank you. Can you, is it working? Okay. Yes, yes, no? We got it, no? Okay. So, hello everyone. So first of all, I would like to thank organizer for a very nice organization and for giving me a chance to present my work. So I would like to talk about energy spectra in a superfluid turbulence, how energy spectra change with different parameters. And this work is based on a numerical simulation, so almost everything that I show would be a numerical simulation. It was done together with Luca Bifarelli, Victor Lvov, Anna Pomelov, Itamar Prokacha, and Ganepati Sahu. So this is, sorry. Okay, so this is the outline of my talk. So we'll start from some general introduction and numerical setups that I use. Then we will talk about energy balance equation and spectra. Then I will give a brief theoretical model about velocity correlation function, because it would be important parameter to understand behavior of energy spectra. And then I will show some selected results for Khomenko and counterflow. In particular, for Khomenko, it would be enhancement of intermittency, and for counterflow, it would be anisotropy of energy spectra. Okay, so let's move to an introduction. So probably it is just too trivial for most of you, so I will move a bit fast in this stage. So this is a simplistic definition of a superfluid that would be sufficient for the purpose of this presentation. Here you have a phase diagram of helium-4. So if we cool it below some critical temperature, which is called lambda temperature, it's undergo a phase transition and become a superfluid. This transition is related to Bose-Einstein condensation. In the condensate, we could have topological defects, and in particular, we are interested in one-dimensional topological defect, which is quantum vortices. So quantum vortices have a few important differences compared to the vortices in a classical fluid. So first of all, they are much better defined structure. They have a fixed core radius in the order of 1 angstrom. They have a circulation around such vortices is a quantized quantity and equal to a quantum of a circulation. And in general, they are just much more stable structures because there is no decay due to viscosity. So in a system we are looking, we have many of these vortices, so thousands and tens of thousands of these vortices. So in fact, we are working with a vortex tangle. And as it was already mentioned in the previous talks, we have many different scales in such systems. So first scale is, of course, vortex core radius. Yes, and depending on the scale, we use a different method. So if we are interested in the small scales of the order of a vortex core radius, and we use a Gross-Petijevsky equation. If you don't care about structure of particular vortices, then it's more suitable to use a BSR calculation or vortex filament models. And if you are looking even in a larger scale, then we are working just with a vortex line density field. And that would be a scale that I will talk about. So just to give you some numbers, this is 1 angstrom, this is on the order of 1 micron, and this is on the order of 1 centimeters. So we have 4 decades separation between each of this stage. Yes, so if we want to describe in this large scale, so the typical choice is Coarse-Grained equation to fluid model. So to remind you what is a two-fluid model, so original two-fluid model was formulated by Landau. So according to this model, superfluid helium can be described as an intimate mixture of 2 fluids. In viscid superfluid, that is described by Euler equation, and the viscous normal fluid that is described by Navier-Stokes equation. So when it was formulated, people didn't know about the quantum vortices, so when they discover it, they include some extra terms. So they include a mutual friction term, a tension force, and if in the system we also have a temperature gradient, then we need to include this term. Okay, so what is a mutual friction and a tension force? If you know coordinates of every vortices in a system, then from microscopical description, we can write this equation and basically calculate a mutual friction. and a tension. However, in a level of descriptions that we are interested in, we don't know this information. We don't know position of every single vortex. So we need to coarse grain this equation and make some assumption about statistics of the tangle. So in the case of mutual friction, it's relatively easy. So typically, this is a negligible term, and then by this term, which can be written as a anisotropy tensor times vortex length density. And from a Biot-Savart calculation, we know that this anisotropy tensor is constant. Also in an experiment, there is many experiments where we measure mutual friction terms, and it's typically proved that it can be described as L times VNS with a constant. For tension force, it's a bit more difficult. We also can run a Biot-Savart calculation and try to coarse grain it. And in certain configurations, for example, in a configuration of a channel flow with a T1 turbulence, it is shown that it has the following form. However, we don't have any kind of confirmation from real experiments. What we have from a real experiment is a bit different approach to get effective viscosity. What they do is look in a dissipation of an energy tangle, and then they have a dissipation of energy, and they just equate it to some effective kinetic viscosity of a superfluid component. So different approaches, but same type of dependence.
So why do you call it tension force?
Why tension force? Because it's basically bending. You can think about a vortex and trying to bend it or stretch it, and that will cost energy, and that's why it is tension force. But I think, I don't know history, but I think historically it's related to tension force in the classical fluids where they have also vorticity and.
Because it looks like more diffusion.
It is diffusion after you do all the modeling, but this is done relatively recently. So this is this is a real expression for that. Say it again, please. What average mean here? Yes, so this is a coarse-grained equation, so we need to define some volumes. It would be large enough to have enough vortices, but smaller than the scales that we are interested in. So typically, if it is a Biot-Savart calculation, then we divide it into some grid and average in every cell separately, and then we have a profile. And yeah, and this was for a stationary state. When I talk about a Biot-Savart calculation, that results for both for this tensor and this modeling was in a stationary state. Okay, so if you worry about what kind of turbulence we could have, so there is basically two main classes of turbulence based on the way we drive it. So the first is mechanically driven. It is very similar to a classical turbulence. In this case, mean flow of superfluid and normal component move in the same direction. That's why it is called a co-flow. Different situation is in a case of thermally driven turbulence. It doesn't have direct analogy in a classical turbulence. So what we have there, we have some heater in the container, and normal component move away from a heater, and superfluid component move towards the heater. So that's why we call it a counterflow. Now people can do many different exotic configurations. So for example, there is so-called a superflow when they use a superleaks and block normal components. So we have flow only of superfluid components, but I wouldn't talk about this type of turbulence. Okay, so equations that I will use would be basically the ones that I showed before with all the assumptions. So for effective superfluid viscosity, we use the ones that taken from experiment, from this energetic approach. For mutual friction is modeled in the following way. We have one parameter omega t, which we can use as a fixed parameter that we put by hand, or we can define it as a root mean square of a vorticity in the system. So it would be still not dependent on a coordinate, but it will depend on time. Okay, so this is numerical setup that I use. We basically do direct numerical simulation of equations that I just showed you in the previous slide. All solution is done in a Fourier space. Resolution is up to 1024 points in each direction. We use a periodic boundary condition in all direction and some Gaussian forcing in small k vectors. So that's it about introduction. Now we can look in a energy balance equation. So energy balance is given by some nonlinear transfer terms, and then we have two types of dissipation. So first is a usual viscous dissipation, and then we also have a mutual friction. So how important mutual friction is? For that, I will show you a result of numerical simulations for, this is a Khomenko for 1.9 Kelvin. So you can see that mutual friction is actually a dominant term for a quite large range of a k vector. So we cannot neglect it, and we need to take into account. It's basically define energy spectrum in this case. Yes.
What's the viscous dissipation for the superfluid?
Why viscous dissipation?
For the superfluid, it's the tension force.
Yes, this is tension force, or from energetical consideration, you can say that. Okay. This is in a large. This is tension in a larger scale, but yes, in a smaller scale, of course, it's a different mechanism. I just showed it that even from a point of view of a coarse gradient, we also get these types of a term with a second derivative. This kind of effective viscosity, yes. And the value actually of this effective viscosity, they are all proportional to kappa. They are all of the same order. It's not exactly the same number like people get from energy description, but it's comparable. Yes, so in this equation, we have 5 control parameters. So we have 2 viscosities, we have 2 mutual friction parameters, and we have a counterflow velocity. So if we try to analyze it, it would be quite difficult because we have a 5-dimensional parameter space. If you try to relate to real experience, it would be even more difficult because all of these parameters will change with the temperature. So maybe it is a good idea to firstly look for some model situation and fix all parameter and change only one in a time. So for so-called symmetrical case where parameters for normal and superfluid components are the same. And this is not completely imaginary situations. It's actually happened for a temperature around 1.9 Kelvin. So for this case, we can look for result of energy spectra. So this is energy spectra. Black line is a result for the usual Navier-Stokes any coupling, and then we increase coupling parameter omega. So what we see is that once we increase omega, energy spectra drops. That's kind of expected, but then after some value, it starts going back again. So why does it happen? If you look into expression for mutual friction, you see that yes, it's proportional to omega, but also it has a cross-correlation function. And this is a plot of a normalized cross-correlation function. So you can see that once we increase omega, 2 velocity fields become more and more correlated, and eventually they basically locked in all lengths. So once they are locked, then the cross-correlation just equal to energy spectra, and this is equal 0. So we don't have a mutual friction. Okay, the situation becomes even more complicated when we add the counterflow velocity. So in this plot, we fix omega, and now we are changing the counterflow velocity. So the fact of the counterflow velocity is basically decorrelating 2 velocity fields. So you can see that correlation function drops. And as a result, it increases mutual friction, and the energy spectra drops. Okay, so I think till now I convinced you that the cross-correlation function is a key ingredient in understanding energy spectra. So it would be nice to have some kind of theoretical explanation for cross-correlation function. But before writing any equation, I will try to explain it in a simple, I will try to explain physics in a simple picture. So imagine that we have eddies of a different size, both in the normal and superfluid components. And if they coincide in the space for long enough time, they will have enough time to correlate the motion. But then we add a counterflow velocity, and you see that the larger, the smaller vortices, the less time it has to correlate. So what we expect that first, with increase of VNS, we have larger decorrelation, and effect is stronger for larger, for a smaller length scale. Yes, and you just seen that effect in a previous plots that I showed. Okay, so now we can try to formulate some theory. We start from our equations, and we move to Fourier space, and then we have a problem. We have a system of two nonlinear equations. We don't know how to solve it, so we need to make some assumptions about it. So one way is how we can do it is to do some uncontrolled approximation. So what we are doing here is we model a nonlinear term by splitting it into some effective decay from this k vector to all other modes, and we model it by a simple relaxation time approximation. So we have some characteristic frequency, which is so this is basically a phenomenological model. We have some characteristic frequency that is related to turnover time of the eddies, and just VNS, just VN or VS, depending on which component we are writing it, and some effective forcing. For effective forcing, we take some delta correlated forcing, which amplitude we still need to find from our equation. So if we do that, after some algebra, we can get an answer for... Say it again? I don't hear. Yes, well, I model it by kind of Langevin forcing and a decay, but yes. So effectively, we have interaction from our mode to all other modes by decay, and all other modes to our k mode by forcing. And we need to find this psi, this phi from equation. Yeah, well, it should be the same. Sorry, it's not the same, but it should be the same. Okay, so if you do all the algebra, that's what we will get. So cross-correlation function can be factorized in this form. So we have ENS0 is basically result for counterflow velocity, for Khomenko. For Khomenko turbulence, when VNS is equal to 0. So what we see from here is that it decorrelates with larger k. So for small scales, we have decorrelated fields, and for large scales, they are correlated. And if we have a counterflow velocities, and we also have this decorrelation function that also is stronger in a larger k, and it's work only in the direction of counterflow velocity. So if cosine is equal to 0, then we don't have this effect.
How do you make a difference in the model between co-flow and counterflow?
When VNS is equal to 0, then it's Khomenko. When VNS is like mean VNS equals 0, then it is a Khomenko. We have mean counterflow velocity. If it is equal to 0, then there is no counterflow velocity. So we have a turbulent part and we have a mean part. So all equations are written for energy of a turbulent component. Okay, so what we get from this theory basically just shows that the correlation is larger in a larger k vector or smaller scale. When we add the counterflow velocity, we have this decorrelation function that also is effective only in a large k and in the direction of a counterflow velocity. So basically all observations that we have in a numerical simulation is confirmed by, well, not confirmed, I would say the theory is confirmed by numerical simulation. Okay, so now when we understand how this spectrum look for kind of real behavior with the temperature of the spectrum. So what is shown here is a result for Khomenko energy spectra compensated on a Kolmogorov scaling for a different temperature. By solid line is shown spectra for normal component, and by dashed line for superfluid component. So it's hard to see any normal and superfluid component are not locked anymore, and same for cross correlation function. So it's very hard to relate to any real experimental results. But we still want to check our theory. So what really people measure in the experiment is typically not an energy spectra. They look in the structure functions. And in particular, they look in the scaling exponent of the structure functions. And the scaling exponent is given by basically by Kolmogorov theory and by some corrections. So if we are interested in the deviation from like Navier-Stokes equations, and we are from a result for Navier-Stokes equations, then we should look in this intermittency corrections. And the good object to explore for that is a flatness, because it just cancels all contribution from Kolmogorov theory and leave only intermittency correction. Okay, so we can measure flatness for different temperatures and different scales, and that's what we have. So in this plot, by black dashed line is shown a result for usual Navier-Stokes, and by colors, by solid color line is shown a result for two fluid models. So what we see here is that, again, we have a non-monotonic behavior. So firstly, it's growing and then going back. But more clearly, it is seen in this plot when we fix a length scale in which we measure and just change in the temperature. You see that we have an and then it goes to classical for a larger temperature and smaller temperature. So how can we explain that? One way to see that is to say that the only difference in our model from a Navier-Stokes equation is a mutual friction. And in a case of small temperature or large temperature, dynamic decides that it is forced by one of the components, is a superfluid or a normal fluid component. And only in the intermediate temperature, where they are roughly equal, the energy exchange is the most efficient due to mutual friction. It is not very surprising that the largest effect is in a region when the mutual friction is the most efficient. Okay, so we have this result. Now it can be measured into a real experiment. So what we did, we contacted a group of experimentators and asked them to measure flatness. And that's what they get. So they measure exponent, this is intermittency correction to exponent as a function of temperature. And as you can see, so this plot is basically just turn upside down the plot that I showed. So they get also enhancement of intermittency on the temperatures that we predicted. So I think this is a very good result. Before, people tried to do something similar in the other experiment, and they didn't get any enhancement of intermittency. So I'm not really experimentalist, so I cannot say why they didn't have it. But my assumption is that in that experiment, they measure it in a larger scale, just because the way the experiment was built. And in a larger scale, as I just show here, the effect is basically negligible. It's very small, or like this. So they wouldn't see any effect. So I'm not consider the result as a contradiction. They probably just measure it in a wrong scale. Sorry? For this one, it's Excimer visualization, so it's in the Florida group.
But that's a very different set of experimental data. On the left, that's optical measurements
Yes.
with a very tiny length of the inertial range. On the right, what it's a pidotubes.
Yes, it's some cantileveration or something like that. but this is, I think this is a better setup because it's not disturbing the system also, and it's allowed to look in smaller scales. But okay, I'm not an experiment, so I probably shouldn't criticize the experimental setup. Okay, another result that I want to highlight would be for counterflow turbulence. So I will show you result for one simulation done in this temperature. So this is a dimensionless parameter of this flow. So that roughly corresponds to the experiment with counterflow velocity of the order of 5 centimeter per second. So what you can see here is that this is a strong coupling regime. So basically, if we switch off counterflow velocity, both components are completely locked. And what we can look at is into anisotropy. So for a long time, people, of course, know that it's intrinsically anisotropic case when we have a counterflow because there is a specific direction. But there was, it wasn't clear how strong anisotropy is. And in many theoretical works, people assume that it is still isotropic because they say that anisotropy, well, of course, this is the easiest way to do, to firstly assume that everything is isotropic. That simplifies a lot of calculation, but no one really knows whether it's true or not. So in this work, we really calculate it and quantify it. So what you see in this plot is a cross-correlation as a function of cosine theta. Cosine theta is angle between VNS and the k vector. So you see that it's dropped dramatically. This is a log scale here. So it's dropped dramatically with the cosine, and the effect become stronger for a larger k vector for smaller scales. And this results into following two-dimensional energy spectra. So all energy in the direction of a counterflow velocity is suppressed, and basically energy is concentrated just along the plane which is orthogonal to counterflow direction. And again, the color scaling here is logarithmic. Yeah, and this is, of course, in a good agreement with our prediction from theoretical model. We could also measure different components of the energy tensor. From this plot, you see that all energy is concentrated in the x component. X is in the direction of counterflow velocity, and it becomes stronger with a larger k vector. So all of this in the k space lead to following picture into real space. So we have a leading contribution to the energy in the streamwise component, but it depends on a cross-stream coordinates. That means in a real space that we have some kind of jets in the direction of a counterflow velocity. Also, y and z component of a velocity field have only large-scale structures, and for Khomenko component, we have a structure of all scales. So all this leads to some kind of quasi-two-dimensional turbulence, which is different from classical two-dimensional turbulence of stratified flows or rotating turbulence. So this is still an ongoing project. We start now to explore the parameter space. We look, for example, how situation change with the temperatures. And for now, it's look like with the temperature, effect become only stronger. So both anisotropy and this also kind of anisotropy redistribution between different element of energy tensor becomes stronger with the k and with the temperature. Okay, to summarize, so we did a number of different numerical simulations and measuring them energy spectra, correlation function, flatness, and so on. And behavior of a cross-correlation function and the structure functions agree qualitatively with our theory. In particular, we show that velocity fields are correlated at larger scales and are decorrelated in small scales. In the case of a Khomenko predicted enhancement of intermittencies that was proven in a real experiment. In the case of a counterflow, we quantify how an anisotropic system is and shows that in fact it is strongly anisotropic and all energy is concentrated in the narrow plane, and that this anisotropy decrease with a decrease in scale, which is very different from what we have in a classical turbulence, because in classical turbulence, with a smaller scale, it becomes more and more isotropic. That's why Kolmogorov theory works at all. In this case, it's not like that. Yes, and if you want to read more about any of this work, about theory or counterflow, here is references. So thank you for your attention. If you have any questions.